Hey everyone, welcome back to my channel, where we've got another installment in our series, I Need Help Understanding. This is where you guys come to me with your deepest questions about physics, math, and engineering. You know what? I can actually get behind this one. This is coming from Michael. He says, how does space-time bend? Does it bend up and down also? How do we know it doesn't just curve around infinitely? So, let's have a look. Here's a star. It has some mass, and therefore it pulls stuff towards it with its gravity. That is, the stuff around here wants to go straight, but the star pulls it towards itself. And so that creates this dip. And this is often visualized as a trampoline with a bowling ball on it. I want to point out, though, that this is not really correct. This is because if you take something like a bowling ball and roll it across a trampoline, then the trampoline doesn't really dip down under the ball. Instead, the ball compresses the trampoline, and the trampoline pushes back against the ball. The reason that things look like they're dipping down is because there's an external frame which doesn't move. If you make the whole thing into a boat and move it along, then everything stays flat. I think what they are trying to say with this trampoline analogy is that the fabric of space-time is flexible. And indeed, the curvature of space-time tells you how massive objects move around. So if you put an object with mass in space, then it will curve the space around it. Now, there are two ways to visualize what's happening here. One way is to draw these arrows which indicate how other objects move around in the presence of the star. If you follow these arrows, then you find that they always end up on the surface of the star. Another way to visualize this is by looking at the distance between 2 points. If we take 2 points which are initially very far away from each other, then we keep them fixed while we move the star in between. Then the distance between these 2 points isn't just a straight line, it becomes this curve. We usually don't use these sorts of visualizations because they're really only good for 2D space. They're good for visualizing how space curves. But space has 3 dimensions. So let's have a look at that. This is a sphere, and this sphere represents a star. Again, it has some mass. If you want to know how the space around this massive object curves, you can use the same method as before. Fix 2 points, move the sphere, and then the distance between those 2 points is no longer a straight line. In 3 dimensions, a straight line between 2 points is an arc of a circle whose center is the midpoint of the 2 points. If the distance between the 2 points isn't too large, then this arc is almost indistinguishable from a straight line. However, if you now add a 3rd point, you see that there are many more ways in which these points can be connected. This one is closest to the sphere, so that distance is shortest. This one goes around the sphere, so that distance is longer. But how about this one? Is this distance shorter or longer than this one? Well, it's exactly the same distance. It doesn't matter how far you go around this sphere, it always takes the same amount of time as going straight. This means that if we connect all these dots, then this distance must be equal to this distance. Therefore, this distance cannot be shorter than going straight. And this distance cannot be longer than going straight either. It must be exactly the same. Now, this makes sense because if you went around the sphere and then continued straight ahead, then you'd end up at exactly the same place. And indeed, this can be generalized to any curved space. If you can go from A to B in one path, then you can also go around a big curve and then continue straight ahead and end up in exactly the same place. So that path must be of the same length. This argument, however, breaks down if you go to 4D space, which is space-time, because now you can go around a closed loop in time and end up in a different place. This is because time is different from space, because you can only go forwards in time, so the length of a path in space-time is defined differently. It depends on whether you go forwards or backwards in time. In any case, we've learned that if you have a massive object, then the space around it curves. But how deep does this curve go? Do you have a surface like here, and then it curves underneath? I hope you can see that the answer is no. The curve doesn't stop at some point. It just continues forever. This is because there's no up or down in space. Space is just space. There's no preferred direction. All directions are equivalent. You can always choose coordinates such that your massive object sits at the origin, and then all the points which describe space around you sit in the x, y, z plane. This means that the curved space extends infinitely far into the negative and positive directions of x, y, and z. The reason that people get confused about this is because we live in space-time, not in space alone. This means that time also plays a role, and you can't just ignore that. There's an excellent paper by Taylor and Wheeler which uses a lot of thought experiments to explain how space-time works and why it curves. It's called Spacetime: An Introduction, and you can find it online. They discuss, for example, what happens if you have two stars. Do they attract each other? And the answer is yes, but not in the way you might think. They attract each other because their curved space around them matches up and continues across the region in between. So the space between two stars is not flat, it's curved. And that curvature causes the stars to move towards each other. So again, Michael, I hope this answers your question. And if you have any follow-up questions, leave them in the comments below. I'm happy to have another look. Yes. It's a little more difficult to make videos on this channel because I have to look up the math before making the video. But I find this a good exercise because it forces me to learn something new every week, and I really enjoy doing this. So keep the good questions coming. One of the challenges of making these videos is that I have to simplify the math a lot, and whenever I do that, there's a risk that I introduce errors. If you want to learn more about general relativity, then you'll need a course that goes into much more detail. But they offer courses on a large variety of topics in science, computer science, and mathematics. I even have my own course there that's an introduction to quantum mechanics, and all their courses are interactive with visualizations and follow-up questions. It's really an easy and fun way to learn something new. Thanks for watching. See you next week.